All right, I'm definitely splicing a couple more of these. We had technical difficulties. I need to make sure I got good black markers for you guys so this is visible. I looked at the video and I'm sure some of you guys are saying, man, we can't even see what the heck he's writing. What's the whole point of this video? But I did learn something. I got a weird looking head, man. All right, so back at it. 9.39, that's way better. Now for this problem, this is just to basically exemplify how these processes are just the same as we did with DC. Now with this problem, everything's already converted into its impedance equivalent. And since it's already in the impedance equivalent, we can actually not know exactly what the true time domain solution is because we actually don't have the angular frequency. If we don't have the angular frequency, we actually do not know. All we have in this problem are basically the impedances and then basically the source in terms of its magnitude as well as its phasing. So let's take a look. So here we started off with 12 at an angle of 0 degrees. And here basically we had a 2-loop circuit in which one loop basically had most of the impedances, but then from the source we did have 4 and then an inductor of the value J20 ohms. And then basically a resistor of 16 ohms. And then a parallel branch containing negative J14 for the capacitor. And then also a series inductor of J25. So considering the series relationship of these two, that would be negative 14 plus J25. And that's actually in parallel with 16 ohms. So if we consider these two, we can get our equivalents here. Obviously, for this problem, we wanted to find the source current. So here we actually have 16, and that is in parallel with negative J14 plus J25. And so all we have to do is just punch this in on our calculator just as the same as before. Negative J14 plus J25 comes out to obviously be J11. So for parallel relationships, 1 over the summation of the reciprocals just as before. So 1 over 16 and then plus 1 over J11. And if we punch this in on the calculator appropriately, we come out with an equivalence of 5 plus 135 plus J7.47. And note the fact that we have a positive impedance here. Because we have a positive impedance, that means that this parallel relationship was resistive and also inductive. So that positive J is indicative of inductance, not capacitance. If we had negative J there, that's when we would actually have capacitance. So now we can actually redraw the circuit, and when we redraw the circuit, we can easily find that source current. So when we redraw this, we're going to redraw this equivalent impedance with a resistor and an inductor, just as we said before. So here we get 12 at an angle of 0 degrees. Here we have our 4 ohm resistor again, and then J20 for our inductor. And with the equivalent impedance, we have 5.135 and then J7.47 for our inductive impedance. And so from here we can just go ahead and easily find that source current by looking at the single series relationship of every element here for plus J20 plus 5.135 plus J7.47. Of course, here we have our source current. So by essentially Ohm's law, or the impedance variation of that, I is equal to V over Z, which comes out to be equal to 12 at an angle of 0 degrees divided by the summation of all of these. So here we would actually have 4 plus J20 plus 5.135 that doesn't even look like a 5, plus J 7.47. And when we calculate, this value comes out to be equal to 0.416 and angle of negative 71.6057 degrees amps. And obviously we can't look at this from the time domain simply because we do not have the angular frequency that all the impedances were calculated from. So we can't find that. The only thing that we can actually determine here is the steady state response, but in its polar form. All right. So let's actually skip over to a couple of the problems in Chapter 10. And in Chapter 10, we're just basically continuing on with looking at this type of method here. And so for here, we're going to maybe do a little bit of source transformation. We're going to utilize a little bit of notable techniques based off KCL. And then eventually we're going to get into the superposition aspect of it. So for Chapter 10, this is problem 1. So the first thing that we have to do, guys, before we actually find, once again, I of t, is to go through and actually convert everything into its impedance equivalent, considering that we have 10 radians per second. So here, ZC, that's equal to 1 over j omega c, which is equal to 1 over j times 10, and then times 1 farad. And that comes out to be equal to a value of negative j 0.1. For ZL, ZL is j omega L. That's equal to j omega L, which is j times 10 and then times 1 Henry. So j 10 and times 1. And that comes out to be equal to a value, obviously, of J10. So now we just go ahead and convert the circuit into its impedance equivalent. So here we actually get to an angle of 0 degrees. Here we have 1. For our capacitor, we had negative J 0.1 for the inductor. We had J 10, and then also our 1 ohm resistor. So if we want to find that source current, all we have to do is just combine these together in parallel. So just as before, punch it in our calculator, it's 1 over negative J 0.1, and then plus 1 over J 10, and then plus 1 over 1. And that gives us an equivalent impedance and value of 0.0101 minus j 0.1 ohms, or ZEQ. So now that gives us a single series loop in which we have 1 and then plus 0.0101 minus j 0.1. And so the source current, I, capital I, is equal to 2 an angle of 0 degrees divided by 1 plus 0.0101 minus j 0.1 ohms. So that was the equivalent impedance in series once we actually combined parallel branches together. And then that source current came out to be equal to 1.97 at an angle of 5.653 degrees amps. Now, here's the thing. That's in the phasor domain, essentially, frequency domain. But we can easily put this back into the time domain by considering that we actually do have cosine 10t here. So I of t is equal to 1.97 times cosine of 10t plus 5.653 degrees amps. All right. So for the next problem in 10.7, this one we could easily just go ahead and utilize KCL in order to actually find the node voltage that we were actually concerned with on this problem. So let's take a look. So 10.7, we wanted to find a node voltage. And in this problem, we actually didn't need to do any conversions. The book already did the conversions into the impedance equivalents already. And so the node voltage that they actually want to find, we just label as Vx. And that's actually going to be not only the voltage across the current source, but also the voltage across negative J 30 ohm capacitor, as well as the 50 ohm resistor. And so the easiest way to find that with this problem, we could utilize superposition here, but let's just actually just go ahead and easily utilize KCL. With KCL, we can just go ahead and write out basically current flowing from the source to node Vx, and then look at these parallel elements as essentially having all different currents. So one equation and essentially one unknown. So I'm going to call this I1. Current flowing from the source through 40 ohms and also J 20 ohms. And here I'm going to say the current source is I2, and then current through the capacitor is I3, and then the current through the resistor as being I4. So by KCL, I1 is equal to I2 plus I3, and then plus I4. Now, current's flowing from the source to Vx, so when we expand this out by basically KVL as well as those current voltage characteristics, then we actually get 120 at an angle of negative 75 degrees, and then minus Vx divided by that impedance of 40 plus J20. And that's equal, if we look at these currents here, that's equal to 6 at an angle, 30 degrees. And then here we have Vx minus 0 divided by negative J30. And then Vx minus 0 over 50. So here we have one equation, one unknown. So all we have to do is break this out in terms of basically all of Vx and then move everything over to the other side. And when we do that, we can easily just go through, manipulate the equation, come out with our calculation of Vx, which is our solution. So here we break this up in terms of essentially 115.91, just converting that over into its essentially rectangular format, minus J31.058 divided by 40 plus J20 minus 5.196 minus J3. Now all that is just a conversion of 6 at an angle of 30 degrees into its rectangular form. And then over here, all we do is took Vx divided by 40 plus J20, moved it over to the other side. And so when we do that, we actually get the coefficient of Vx of being in the form of 1 over 40 plus J20 plus J30, and then plus 1 over 50 times Vx. And so from here, we can actually rewrite Vx in terms of being equal, once we solve for everything on the left side, and then actually get this equivalent impedance here, then we actually get the following. We get negative 3.1885 minus J4.7805, all divided by 0.04 plus J.0233. And then that comes out to be equal to 124.08 at an angle of negative 154 degrees volts. So this is actually what we end up getting due to the fact that we not only have the voltage source on the left, but also considering that we do have this current source that's actually driving a high value of voltage here. Okay. So let's do a little bit of source transformation and see if that actually helps us in terms of deriving maybe an easier solution. So we're actually going to do KCL once again with 10.13, but we're just going to do it in such a manner that we can convert the circuit to allow us to basically write our equations very, very, very simply. So here for 10.13, we actually want to find the voltage across the 3 ohm resistor. Okay, so for here, if we actually don't consider source transformation from the parallel resistance of 10 ohms and then also the current source of 5 at an angle of 0 degrees, then essentially we would actually have 2 equations, 2 unknowns. But with source transformation, we can convert this over and essentially just have one unknown node voltage, which is exactly what we're actually looking for the voltage across the 3 ohm resistor. So let's go ahead and convert this over. We convert this over into basically its voltage source equivalent. That would actually put the 10 ohm resistor in series with 8 ohms as well as J6. So let's go ahead and convert this over. Make sure that we understand and also remember how to do source transformation very efficiently. So obviously with source transformation, all we did was take 10, multiply it by 5 at an angle of 0 degrees. That puts the 10 ohm resistor in series and gives us a voltage source here of 50 at an angle of 0 degrees volts. So the voltage of Vx across the 3 ohm resistor is easily just denoted as not Vt, but a Vx, basically a node voltage. And so now we can just basically apply KCL and then easily just write our KCL equations. We'll have one unknown node voltage, easily just solve with one equation. So I'm going to denote, because we have a voltage source on the left and right, I'm going to make the assumption that my currents are going to flow in this manner. So I1, then I2, and I3. And so from here I can write out my KCL equation. So I1 plus I3 is going to be equal to I2, current in is equal to current out. So I1 by KCL, I1 plus I3 is equal to I2. So here we have 40 and angle of 30 degrees, current's moving from the voltage source going through the negative J2 capacitor. So minus Vx divided by negative J2. And so from here, that's going to be added on. Current's moving from the 50 at an angle of 0 degrees voltage source through the equivalent impedance all to Vx. So here we actually have 50 at an angle of 0 degrees minus Vx, and then over 18, and then plus J6. 18 plus J6, because here we have 8 ohms as well as 10 ohms, and that's in series, so we just add those. So add the rectangular values, plus J6. And then that's all equal to Vx minus 0 divided by 3. Current flows from the node Vx all to ground divided by 3 ohms. So here we have just one equation, one unknown, just like we did in the prior problem. And so if we go ahead and move all of our scalar, well, not scalar values, but move all our source values over to the other side, and then move basically the combined variable of Vx over to the right, then we have one equation, one unknown. So here we have 40 at an angle 30 degrees divided by negative J2 plus 50 at an angle of 0 degrees divided by 18 plus J6. Move Vx over to the other side, and then we get Vx, and then times 1 over 3 plus 1 over 8 plus J6 minus 1 over J2. And so here we can go ahead and combine those values in, punch them into your calculator, and then once we actually solve for Vx, Vx actually comes out to be equal to 29.36 at an angle of 62.88 degrees volts. Now, obviously, once again, we don't have the angular frequency. So if we don't have the angular frequency here, then we absolutely don't have any ability to know what this thing looks like actually in the time domain. So the only thing that we can do is solve for the solution of Vx within its phasor equivalent. Now finally, for chapter 10, for this problem, we're going to look at basically an introduction into source transformation. But we're going to look on that at the next video. I'll be back.